ending with a bright galaxy, minor mergers are there. This is a dark matter halo that I call primary, in which a stellar gaseous disk, a bulge, and a massive black holes are embedded. And this is a second, lighter dark matter halo, my secondary, my satellite, is still hosting this bulge and a black hole. They are going to interact and give rise to a minor merger. We have the freedom to choose the masses of the two interacting galaxies, and so the mass ratio of the two galaxies, and so the mass ratio of the two interacting black holes. And we are guided by the Monte Carlo simulations of merger trees that are telling us that as a function of redshift for a given model of black hole evolution, you have that around redshift 5, you have typical masses for the primary black hole just of about 10 to the 5 solar masses, and mass ratios that at the beginning are comparable to unity, but due to the diversity that is created in the masses along a merger tree, mass ratios of the order of 0.1 start to develop again at the redshifts where Lisa will be probably operating and seeing these quite high redshift events. So, So we decided to study minor mergers because we would like to mainly answer the spectrum question. Does nature provide the mechanisms that are conducive to black hole coalescence in minor mergers? And this is a difficult question because we don't have the answer also for major mergers. And the difficulties are similar. Here we can distinguish also in a minor merger 3 different dynamical phases. We have the pairing phase where the two black holes are passively following the dynamics of the disks in which they are embedded. Then once the merger is to its end, we may form a binary when the massing stars and gas enclosed in the orbit of the two black holes is less than the mass of the black holes themselves. And this is occurring on a scale which is mainly scaling the black hole mass ratio to some power. So if for a major merger this is, say, a few parsec, for a minor merger we have also to explore even smaller distances. And this is also holds true when we want to bridge and enter the gravitational waving spiral domain. So we have to really enter distances that are less than a milliparsec before we can produce a laser source. In my talk I will focus mainly on the pairing phase, mainly because our numerical simulations are limited in force resolution, and so I will be talking on the dynamics of pairs on scale above several hundreds of parsecs, and if I have time I will then mention problems of recoiling black holes in these galaxies. So just to understand the diversity between minor and major merger, let me just pop up briefly and make a summary on what we know about major gas-rich galaxy mergers, considering just the transit from pairing to binary formation. We know, and we already heard, that dynamical friction guides the black hole pairing on large scales. So dynamical friction is telling you that if you have a massive body which is moving in a background of stars or gas, is subject to a deceleration, a drag, which is resulting from the fact that this body has risen over density due to its gravitational pull. And the drag is stronger the bigger, the larger is the density of the background is very high when the velocity of the perturber is comparable to the stellar dispersion velocity or the sound speed in the gaseous environment, and also it is proportional to the square of the black hole mass in this case. Clearly, this formula cannot capture the entire physics of a merger. So numerical simulations are really suitable tools for learning about the dynamics of the black holes that are moving in a background which is time-varying. The holes also carrying along a much larger effective mass in these early phases once they are bound to the binaries and the disks. Here, this is an old picture. I'm sorry, most of you have seen it, but I want to stress here that these are the gaseous disks that we see once they have already reached a reasonably close separation in a one-to-one major merger. These are the gaseous disks that have been sinking against the dark matter halo. They have been tidally perturbed, and a bar instability we see is excited in the stellar disk, which is driving around the two black holes two nuclear gaseous disks weighing 10 to the 8 solar masses. So we have 10 to the 8 solar masses of gas around, say, a million solar mass black hole. In this very moment, the black holes are carrying a much larger effective mass, and this is the reason why this will be conducive to the rapid birth of a black hole binary. When we wanted to follow the dynamics on smaller scale, say below 100 parsec, we have to zoom in and simplify the physics, and in particular the thermodynamics and radiation physics of the gas, that in the N-body simulation, as well as in this AMRI simulation that Lutromeyer has recently carried on, we simplified, I was saying, the physics by taking a polytropic equation of state for the thermodynamic of the gas with an index which we believe is capturing the fact that in this gas there is an ongoing burst of stellar formation and supernova feedback. So the gaseous environment is relatively warm, and in this environment the two black holes are indeed binding and form an eccentric binary. Here you can see the black hole separations versus time. Here we have already reached the scale of 0.1 parsec.
Sorry, can you just tell us what scale? It's hard to read the axes there.
Yes, I have still difficult. This is, well, let me see.
You can't read either.
It's 100 parsec, and this is 0.1 parsec. I'm sorry. So you see that really you have formed a binary in this gaseous environment. If you make the gaseous disk hotter, you delay somewhat the formation of the binary because, of course, the density of the background is lower.
How big is the disk at this point? Sorry?
10 to the 9 solar masses, because at the end of the merger, you have been really able to build up a massive rotating nuclear disk.
And physically, what radius
the
is that?
The size is 100 parsecs or so. Okay, let's now move on minor mergers. Again, dynamical friction is guiding the early phase, but remind that now if we are dealing with a black hole embedded in a stellar and gaseous disk and in a bar that is much smaller in this case, so we have a weaker effect of dynamical friction, means longer times. And also given the large mismatch in the masses of the interacting galaxies, there's a new effect that is coming into play. Parallel forces are trying to shock heat the satellite and stir up and destroy stripping gas and stars during the encounter, which is mainly not present in a major merger. So here I'm reporting on a set of simulations that Monica Colpi has carried on considering disk galaxies that are mainly rescaled replica out of redshift 3 of a Milky Way-like halo. So we have a halo, a disk, and a bulge. We let the gas fraction vary from 0 to 50%, and these are just the masses of the black holes in the primary and in the satellite galaxy. You can clearly see that a minor merger is really not very aggressive concerning what is happening onto the primary galaxy. And you can clearly see that the satellite is mainly disruptive. So it is profoundly different from a major merger. But let's go into the detail. Consider now a coplanar prograde parabolic encounter and focus now on the slight solid line. Here we see the black hole separation on kiloparsec scales versus time, and you see that mainly the black hole, this relative distance is reducing, but not much, and there is a sort of stalling at around 2 kiloparsecs. When we look also at the environment of the black hole, we find that mainly a gas-free satellite cannot dissipate energy by tidal shocks and is really tidally stripped. And so we leave this black hole wandering around 2-3 kiloparsec in the plane of the primary galaxy. By contrast, if we add a gaseous component, we see that at some point after a few pericentric passages, this is a quite eccentric orbit, mainly the black hole separation went down to our force resolution limit. And so we believe that in a gas-rich environment, the second black hole may probably reach a separation where it can become a successful binary. Doing back of the envelope calculation at that distance, the dynamical friction time is still less than the Hubble time, and even though we do not continue our integration, we expect that the secondary light black hole will eventually bind to the primary. But let us really understand more in detail what is really going on here. If we look at the stellar distribution of the satellite, we witness a sort of episode of star formation due to inflows by compressive tides. Once this episode of star formation has occurred, the gaseous disk mainly develops a clumpy, irregular, multi-phase structure and is largely turbulent. It is just because of this steepening of the density profile that the black hole can really, together with the bulge and the disk, can really go deeper into the disk of the primary and so proceed more effectively on its way toward the formation of the binary. Here I'm showing in this plot the cumulative mass in new stars that has been created after the third pericentric passage. Thus, an enhanced star formation in the central region compared to a satellite model that is allowed to evolve in isolation. And this is mainly the reason why the black hole could really become closer and closer to the primary. Then if we follow the subsequent evolution, there's a phase, the one here depicted in gray, where run pressure stripping by the gas of the primary galaxy expels the gas which is present in the satellite. And so at the end of our simulation, we see that the satellite is now a sort of cuspy gas pool stellar system with a central black hole. If we change the geometry of the orbit and with the same gas fraction, 30%, we follow a retrograde coplanar gas-rich merger. Due to the fact that in a retrograde encounter, the relative velocity between the satellite and the primary is bigger, you are weakening the effect of the satellite is subject to repeated shocks that are eventually disrupting the satellite itself. And so we are left with a sort of bare, wandering black hole. So geometry matters regardless the gas content. Nature is continuous, and so if we simulate under rather different condition a 1-to-4 merger, we see that after the secondary Astron passage, the stellar disk of the satellite is subject to a bar instability. A bar instability that, remind, was also present in a major merger. A bar instability that is also excited in the gaseous component, which make mainly the environment of the black hole much denser and stiffer. So even with a gas fraction of 10%, the black hole separation goes down to our force resolution limit. And so in this relatively, say, gas pool environment, in a 1-to-4 mass ratio, we expect that the black hole will eventually form a binary. So I really, the message that I want to deliver here is that in minor mergers, the early phase of black hole pairing is quite sensitive to the gas content and encounter geometry. So we may find some obstacles, we may have fade binaries or binaries that will form on a delayed time scale. So this is the obstacle that we find here. Remember, yesterday we were instead saying that for a major merger, the clear obstacle we encounter is in between, say, 0.1 parsec down to 0.01 parsec, when we are not still able to model the gaseous disk and the stellar disk, which is forming during the in spiral and the hardening of the binary. So this is something that goes into, a question we would like really to answer, is the parameter space for LISA exploration reduced? Is there a limiting value of Q? Probably we won't be able to pin down a limiting value of Q because it depends on gas content and geometry. So there will be a range of parameter space that will be conducive to binary and probably to coalescence, and we really have to work it out more properly, but it is clear that the successful event, a LISA event, requires a lot of gas that was present probably only in the halo out of very large redshifts. And the results are going into the direction that is indicated by a recent work by Bellovari et al. They have followed the sort of dynamics of black holes of this size from a straight cosmological simulation while they were trying to build up a Milky Way halo. And so they found that there are, for a Milky Way halo, roughly 10 black holes that are wandering in the halo, and this is the distribution in distances below a few parsec up to thousands of parsec, and these have been the orbits that have been traced along this straight cosmological simulations. This is not that has been performed. Can we associate during a merger an AGN activity? Can we see a dual AGN, a binary, or a burst prior to coalescence, or even a recurring black hole in a disk galaxy? Because remember, this minor black hole hasn't really produced a severe damage on the spiral. Certainly, it will have created over densities and distortions in the velocity field, but it is primarily still a spiral galaxy. We have been trying to follow also the accretion history by using a subgrid physics, and this is a key point, and bonding coil accretion prescription. But let me say that I believe one of these two results. If I just follow the black hole growth along the sinking of the black hole, and I plot the mass ratio, so the mass ratio of the secondary relative to the primary, when there is this transformation episode, we see a rise in this mass ratio. It means that the secondary is really gaining mass, and this is the mass versus time of the satellite, while the primary is accreting as the galaxy would be in isolation. And here we can show that really we can map the gaseous particles and see that they are really losing angular momentum. And so maybe we cannot say much on the m dot, the actual m dot on the black hole, but there will be probably on kiloparsec scale as activity that has been triggered. Later on, when the black hole is already well embedded inside the disk of the spiral primary, then, well, this, I skip it, the black hole orbit is going to circularize. This is something we approach also with Massimo Droffi. When you have an eccentric orbit in a rotating Gaussian or stellar background, the orbit gets round, then you minimize the velocity relative with the gas, which is in the spiral arms of the primary, and you might have, again, an accretion episode, but this really depends on the way we model accretion. If we change the gas fraction and just focus on the associated AGN activity when we have the starburst, we do see that the black hole mass ratio increases. So this is a good news, because if the mass ratio of the black holes, so if the secondary black hole gets more massive, dynamical friction will become more effective. And so I will help the subsequent dynamical history of the black hole, because then I may successfully form a binary. And so the message here is the mass ratio of the black hole can rise and then affect the subsequent dynamical evolution. But if I change the encounter geometry for the same gas fraction, I consider an inclined merger, then, for instance, I focus on just these two red lines. The episode of star formation has weakened, and so also the AGN activity and the gas inflows have become weaker and weaker, and I may not see any double black hole. I skip this. And so let me just conclude by saying that minor mergers can give rise to episodes of accretion, but clearly they depend on the geometry and the gas content, but we can still see offset nuclei, and I'm here reporting the only known case of, this is a serendipitous discovery by Bath, where you see a spiral and some blob here, which is a Seifert nucleus, which really seem to spiral inward, and this might be the only case where we do see a minor merger in action. Can I have 1 second for the speed or the question time? Suppose now that a minor merger is conducive to a coalescence event. Should we really expect a recoiling black hole? Well, we know that for equal mass mergers, the distribution of recoil's velocity that we extract from a flat distribution of spin and equal mass black holes can either be peaked around 10 kilometers per second. This is referring to the case where the spins of the two black holes are parallel and fully aligned. In the isotropic random case, we might have much bigger recoils because the spins are oriented randomly. And as we shown with Massimo, in a gas-rich environment, gas is producing alignment and is still reducing the magnitude of the expected recoil at statistical level. But I want to remind you that the kick velocities goes like the black hole mass ratio to the square, so I would expect that in minor mergers, the kick velocity is nearly zero, and so I really would expect that in minor mergers and in spiral, we should not find any recoiling black hole, and this goes into the line that Stephanie has indicated. We should go really to look for recoiling black hole in large ellipticals, and I leave here my conclusions.
So you mentioned the prospect of the secondary gaining mass, and so getting to a closer to unity mass ratio. I wonder if you could comment on a paper posted a couple of months ago by Holly Bachman et al., where they actually look at sort of the cosmological evolution of these and conclude that you can get surprisingly different masses in ultimate mergers because the original mass ratio is actually kind of close to unity. As time goes on, they can actually become farther and farther apart. So do you believe that result? If so, what are the differences in assumptions?
I think that the answer, since I'm still worried about my result, I don't know if also Holly Bachman should really be worried about this. Let me just make a short comment. In a numerical simulation, you don't have the resolution to really map the accretion onto the growing black hole, as in our case. So it depends really quite much on the recipe you are using, and so maybe we should really reconcile. I don't know what is the recipe she used. So let me just say that we have an indication that this screw ratio is time varying along the course, and this really should be kept in mind. What is the magnitude of the change depends on our way we model the physics, and I was just having this transparency that is mainly telling us that we are still confused unless we use unless we are able to resolve the black hole sphere of influence and then follow the dynamics of the gas within this radius, which happen to be possible with Massimo simulations. But as far as you rely on this cosmological large-scale simulation, you may have several choices, and as was mentioning also Giuseppe Lodato, Hopsink and Carteret came out with a nice formula for the accretion rate on large scale, which is just purely dynamical. So we have really to go into the detail, whether we are looking in a region where the black hole is dominate, where instead the mass of the gas is dominate, and decide then what is our accretion recipe. And we have to do it for the next several years because it's complicated.
Okay, so one more